I'll finish off the rest of the coverage for Module 2B in this second part of the video lecture. But first, let me introduce the charge balance equations and the framework for solving problems involving multiple equilibria. Then we'll jump off to some examples of problem solving and we're done. Charge balance equations. Electrolyte solutions are electrically neutral even though they may contain many millions of charged ions because the number of mole per liter of positively charged ions is equal to the number of mole per liter of negatively charged ions. This equation represents the charge balance condition and is called the charge balance equation. Let's go through some example of this topic. Write a charge balance equation for the system described in exercise 2. That system is this. The CBE is just a collection of the concentration of positively charged ions on one side and concentration of negatively charged ions on the other side. Remember, though, that a charge balance equation is based on the equality in molar charge concentrations, and that to obtain the charge concentration of an ion, you must multiply the molar concentration of the ion by its charge. Meaning, imbes nga molarity sa ions lang ang i-encode sa CBE, i-multiply nato ang equilibrium concentration kung pila ang mole sa charge. Example, sa Na plus times 1 ang iyang equilibrium concentration, kay 1 mole ang iyang positive charge. Sa Mg2 plus times 2 ang iyang equilibrium concentration kay 2 moles ang iyahang positive charge. So let's see that on the next example. Write a charge balance equation for the system shown here. So the answer is H3O plus equal to HSO4 minus plus 2 times the concentration of SO42 minus because the charge here is 2. We already know how to write equilibrium constant expressions, MBEs, and the CBE. So we'll try to use them to solve a multiple equilibria problem. We'll use this framework to guide us in every step towards solving a problem. So first, we should write the mass balance chemical equations, then set up for the unknown quantity. That means we have to identify the unknown. What is asked in the problem? And then from the balanced chemical equations, the equilibrium constant, the mass balance, and the charge balance expressions. After doing all that, we should be able to obtain equal numbers of unknown and the number of independent equations, because if we can't do that, the problem is unsolvable. But with the equilibrium constant expressions, MBEs, and CBE, that equal number of unknown and independent equations is possible. To make the calculation simpler, should make suitable approximations, and then proceed to solving the equations for unknown. After solving, we should try our approximation if it is valid, because if it's not, we should go back to step 7, making suitable approximations, and then proceed to step 8, step 9, and that should bring us to our answer for the unknown. So let's try this exercise. Calculate the molar solubility of MgOH2 in water. Step 1. Write the pertinent equilibria. From the problem description, chemicals that are involved is that of MgOH2 and water. We should be able to write the balanced chemical reactions from those two chemicals. So we have these two equilibria here. Step 2, definition of the unknown. We are asked to calculate the molar solubility of a solid. The molar solubility of a solid is usually equal to the equilibrium concentration of one of its components. So here I chose the concentration of Mg2 plus as the solubility of MgOH2. Step 3, we can draw Ksp from the balanced chemical equation of the dissociation of the solid, and then the Kw from the dissociation of water. Step 4, write the balanced chemical equation. So this is the mass balance expression for our equilibria. How was this obtained? Let's go back to the balanced chemical equations. We can see that OH minus is produced from the dissociation of two chemical species, that is MgOH2 and H2O. But we can't include those two in the MBE because they are solid and liquid. So we'll use Mg2 plus and H3O plus as the source of OH minus. Next, charge balance expression. Charge balance expression is just a collection of negatively charged ions on one side and positively charged ions on the other side. So we can see here that MBE and CBE are the same. Step 6. Count the number of independent equations and the knowns. So we have 3 independent algebraic equations and also 3 unknowns, which are Mg2 plus, OH minus, and H3O plus. Step 7. Make necessary approximations to make our life easier. If we examine the sources of OH, we can identify 2, MgOH2 and water, whereas the source of H3O plus is only one, that's water. So we can assume that the concentration of H3O plus is very small compared to the concentration of OH minus. Therefore, the mass balance or the charge balance expression can be simplified into concentration of OH2 equal to 2 times Mg2 plus. This equation here is just the Ksp expression where the value of OH minus is substituted with the value that was derived during approximation. That value is the concentration of Mg2 plus times 2. Now, to get the solubility of the solid, we have to combine all similar terms. Since we have Mg2 plus outside the parentheses and Mg2 plus squared inside the parentheses, all in all, we have Mg2 plus cubed. 4 there is from 2 squared. We are only interested with the concentration of Mg2 plus, so we have to get rid of the cube and 4. So we'll divide both sides of the equation by 4 and also perform cube root on both sides. That will give us the concentration of Mg2 plus or the solubility of our solid, which is 1.21 times 10 to the power of negative 4. After that, since we made an assumption, we should check if our assumption is valid. So we go back to equation in our assumption. So the concentration of OH minus is equal to 2 times the concentration of Mg2 plus. So just substitute the concentration of Mg2 plus that was calculated, which is 1.21 times 10 to the power of negative 4 times 2. That will give us 2.42 times 10 to the power of negative 4. Now, our assumption was the concentration of H3O plus is very small compared to the concentration of OH minus. So we have to prove that. In order to do that, we'll calculate the concentration of H3O plus from Kw expression. So just substitute the concentration of OH minus and the value of Kw. Then solve for the H3O plus concentration, and that will give us 4.1 times 10 to the power of negative 12. Compare that to the concentration of OH minus, which is 2.42 times 10 to the power of negative 4. Now, it is obvious that our assumption that the concentration of H3O plus is lesser than the concentration of OH minus. So, our assumption is valid. So that's how we calculate problems involving several equilibrium following the framework. Let's try another exercise. Calculate the molar solubility of calcium oxalate in a solution that has been buffered so that its pH is constant and equal to 4. And always write the balanced chemical equations. From the problem description, it says that we have calcium oxalate, which is a solid, and it can dissociate into Ca2 plus and C2O4 minus. Now, in water, C2O4 minus can interact with water to form HC2O4 minus and H2C2O4. Thus, we have another two balanced chemical equations. This chemical equation 2 here is for the interaction of oxalate ions with hydronium ion of water. And then this chemical equation 3 is the interaction of hydronium ion with the resulting HC2O4 minus. And of course, since we are dealing with aqueous solutions, we should include the dissociation equilibrium of water. Step 2, define the unknown. So again, the unknown for our exercise is the molar solubility of a solid, which is equal to the concentration of one of its components. And I chose Ca2 plus concentration as the value of our solubility. Step 3, set up the equilibrium constant expressions. For the first chemical equation, the equilibrium constant expression is that of the Ksp, then followed by the K2 expression, which is an acid dissociation constant expression similar with K1, and lastly the Kw expression. Step 4. Because CaC2O4 is the only source of all oxalate-containing species, the concentration of Ca2 plus is equal to the concentration of oxalate-containing species, namely equilibrium concentration of C2O42 minus plus HC2O4 minus plus H2C2O4 minus. Moreover, the problem description states that the pH is 4. The expression of pH is equal to the negative log of H3O plus. To extract the concentration of H3O plus, we have to get the antilog of negative 4, and that would give us 1 times 10 to the power of negative 4. Calculating for the concentration of OH minus using that value of H3O plus in the Kw expression will give us the value of OH minus equal to 1 times 10 to the power of negative 10. Next step, charge balance expression. Now, the system is buffered to pH 4, but the components of the buffer was not mentioned. So there's not enough information to write charge balance equation. Next, we'll count the number of independent equations in the unknowns. So we have 4 unknowns and 4 independent algebraic relationship. Since we have equal number of unknowns and independent algebraic equation, that should allow us to calculate for the unknown. Step 7, there's no need to bother with the approximations and go directly to step 8, which is calculating for the unknown. Now, we need to get the concentration of Ca2 plus as our solubility, right? So we will use the Ksp expression to do that. Now, in the Ksp expression, we have another variable which is C2O42 minus. So we'll use MBE. In the MBE, indeed, we have C2O42 minus, but there are other variables that are introduced here. So we have to solve for the values of those variables. First, I will use the K2 expression. In the K2 expression, we can find C2O42 minus, and also HC2O4 minus. We'll just have to manipulate the equation so that we'll get HC2O4 minus on one side and all other variables on the other side. Now, if we get that equation, we'll have to substitute for the numerical values of H3O plus and the K2 value. And that would give us 1.85 times the concentration of C2O42 minus. Now we can use that equation to update our MBE. So the MBE will become the concentration of Ca2 plus equal to the concentration of C2O42 minus plus 1.85 times C2O42 minus. And we are left with last variable H2C2O4. To get the value of H2C2O4 in terms of C2O42 minus, we'll use the equation 3 again to substitute into the K1 expression. Here, since we have HC2O4 in K1 expression, we'll substitute that with 1.85 times C2O42 minus, and then again, we will manipulate the expression to give us H2C2O4 on one side and all other components or terms on the opposite side. Then substitute the value of H3O plus and K1 value, and that would give us the equation 4. Now, if we update our MBE, and our MBE will become Ca2 plus equal to the terms of C2O42 minus. So combining all that terms, we'll get 2.85 times C2O42 minus, and we'll use that expression of C2O42 minus to substitute into the KSP expression, and our KSP expression will now be in terms of only one variable, which is Ca2 plus, and then we can now solve for the solubility of our solid. And that's all for Module 2B. Please accomplish the monitoring form for these video lectures and send to me your question, queries, clarification, and other concerns. Thank you for listening.